everything will be important in every class hereafter. So today we are going to start a shell energy balance. So in first part, if you remember, what we have covered is a similarity between heat transfer, mass transfer, and momentum transfer. So where we have discussed Newton's law of viscosity, and then Fourier law of heat conduction, Fick's law of diffusion, then Finding equation, and then Newton's law of cooling, and then Slattery equation, and interface flux and everything. So we have convinced that, hope everybody is convinced that heat transfer is similar to mass transfer is similar to momentum transfer. And then in second part, what we have done is shell balance for a momentum transfer. So momentum transfer we have considered. Now exactly same, using same logic. Now you know that heat transfer is similar to momentum transfer with some similarity, some differences and everything. So we have established the relation between heat transfer and momentum transfer, and we had in detail discussed the shell balance approach for momentum transfer. Same analogically, now you can use that shell balance for heat transfer also. So this will not be a first class on shell balance, energy balance, okay? So this in continuation with momentum transfer, all the input from momentum transfer can be directly used in heat transfer, because we know that heat transfer is similar to momentum transfer. Similarly, we will go for mass transfer. That time also same logic holds good. So shell balance for heat transfer, mass transfer, everything will be applied to shell balance for mass transfer. And we'll have just a brief, you can say, now maybe in say 4 or 5 classes we'll complete this shell energy balance, but it is not just a 4 or 5 classes. All the information which we have discussed in shell momentum balance can be analogically applied to a shell energy balance also. So so this shell energy balance equation. So initially what we'll start in heat transfer also. So we'll start with the simplified balance equation. So maybe a temperature variation only in one direction. If temperature variation is there in more than one direction, then you can directly use the equation of change for non-isothermal system. Okay, so equation of change for heat transfer actually. So here we are looking into problems where we have temperature variation only in one direction. So what is overall shell balance equation? And this shell balance equation is again for steady state. Okay, this shell balance equation, shell energy balance equation is for steady state. So overall rate of energy coming in my differential shell minus rate of energy out from my differential shell plus generation and consumption by any say chemical reaction or everything, that equals to 0. That equals to accumulation actually for unsteady state. For steady state, accumulation will be 0. So what will be the all energies coming in my system? It will be either by convection, then it can be by conduction, it can be by work done also. That everything is discussed here. So this is the rate of energy in by convective transport. Convective transport means it will be characterized by the bulk motion and heat content per unit volume. That will give me a rate of energy coming in by convective transfer. Then rate of energy coming in by molecular transport minus rate of energy going out by molecular transport. This will be conduction. The rate of heat coming in by conduction, rate of going out, heat going out by conduction. And third is, if there is a molecule, here also here you can see, here also you have molecular transport, okay, and the physical meaning of this molecular transport is conduction, is molecular level, okay, molecular transport. But here molecular transport means movement of molecules, okay. So rate of work done on the system by molecular transport means this is movement of molecule. If molecules are moving from one place to another place, then there can be either work done by the system or on the system when molecules are moving within a systems. That rate of work done. So work, you can say work is also form of energy. So rate of work done on the system by molecular transport. So this molecular transport and this molecular transport are slightly different physical meaning. This molecular transport means on the level of molecules, without the motion of molecules, whatever with the energy is transported is conduction on molecular level. But here work done on a system by molecular transport means if molecules are moving, okay, so all the time this convection is associated with this rate of work done. Wherever there is a convection, there will be a rate of work done on a system by molecular transport, and there can be a rate of work done by the system. If on the system, energy will be added to a system. If it is by the system, energy will be removed from the system. So this is the rate of work done on the system by molecular transport, rate of work done by the system by the molecular transport. Then we have any external agency. Okay, so you can have compression, you can have heat addition, you can have heating and everything. So that time also energy will be added. If say there is a compression is there, there is a friction is there, so rate of work done on the system by external forces, any external forces, this is work done on the system by molecular movement of the system itself, but this is from external agency. Okay, so if I'm adding the heat, I'm adding the heat to system or removing the heat, that can be accounted as a work done, or I'm compressing the system or expanding the system, again work and energy will be associated with, that will be this actually rate of work done on the system by external forces. And you can have rate of energy production. There can be a chemical reaction, there can be electrical, you can say electrical, this thing is there, electrical resistance is there, because of energy can be produced and all. So that will be there, that equals to zero, that equals to zero. So this is overall energy balance equation. So you can see this is energy added, this is energy removed, this is energy added and removed. Okay, this is energy added and removed by external forces. Okay, and this is the generation and consumption. You can say this is generation and consumption. Rate of energy production means it can be generation also, it can be consumption also. This is also rate of work done on the system by external forces. It can be positive also, energy added to system. It can be negative also, energy removed from a system. If cooling is done, so energy is removed. If heating is done, energy is added. If I'm compressing the system, there is a compression in a system, then energy is added. If I am expanding a system, energy is removed. So that will be accounted here, and this will be always associated with this. So this convection will be always associated with this, and this will be conduction. So this will be rate of energy coming in by convection, out by convection, in by conduction, out by conduction. Whatever be the work done because of molecular motion of the system, that will be on the system by the system, and this will be external agency, and this will be energy production, that will be equals to zero. And this zero is true for steady state. If I have unsteady state, then there will be accumulation of energy. Okay, at steady state there will not be any accumulation. Accumulation term will be zero at steady state, hence it is equals to zero. So overall energy balance will be just one more term will be added here, that will be actually accumulation. Energy coming in minus going out plus generation minus consumption. So these two terms account for generation and consumption, it will be equals to accumulation. This is overall energy balance equation. Okay, so you can see there are similarities and there are differences also. There are similarity as well as differences from shell momentum balance and shell energy balance. Only now you need to all the time attentive what we have covered in momentum transfer, what we are covering in energy transfer, how energy and momentum is similar, how energy and momentum is different, and how that information can be used here. What additional precaution need to be made, that okay, so we will not logically extrapolate some wrong information so that we will get a wrong model in energy transfer. That all the time you need to be attentive. So this is overall shell energy balance equation. Now next step is boundary condition. So this is clear to everybody? Okay. So next is a boundary condition. Okay, so boundary condition. So now you can see exactly logically similar. A temperature may be specified at the surface. So this boundary condition is similar to which boundary condition in momentum transfer? Roll number 1, Abhinav.
Yes, sir.
Yeah, this boundary condition is similar to some boundary condition in momentum transfer. Temperature may be specified at the surface. Now you are correlating momentum transfer with the heat transfer. Temperature may be specified at the surface. So any similar boundary condition have we discussed in momentum transfer? Which property is similar to temperature in momentum transfer?
So flux.
Flux is similar to temperature.
No,
Flux
sir,
momentum,
velocity.
velocity. So you are answering like you are attending first class in transport. So velocity is similar to temperature in momentum transfer. So here temperature may be specified at the surface. This is first type of boundary condition you may encounter in heat transfer. So what will be the boundary condition in momentum transfer then?
So no slip boundary condition.
Yeah, very good. Very good. So more precisely, that can be spelled out like velocity may be specified at the surface. Okay, velocity may be specified at the surface or at the interface. So you can see there is a similarity also, there is a differences also. Here temperature is specified at the surface. So here surface itself is understood as an interface, but in momentum transfer it is precisely interface. Velocity at the interface between solid and fluid, that has a no slip boundary condition. So no slip boundary condition, so velocity may be specified at the surface, and that is spelled or that is defined in momentum transfer as a no slip boundary condition. Okay, so you can see this boundary condition is exactly similar to that boundary condition. Then second boundary condition, okay, second boundary condition is the heat flux normal to surface may be given. Okay, this is equivalent to specifying the normal component of temperature gradient. So roll number 2, Abhishek.
Hello, sir. Hello.
So what boundary condition will be equivalent of this B type of boundary condition shown on your screen?
Liquid gas interfacial fluids, zero flux condition.
Yeah, zero flux condition. Flux may be given, momentum flux may be given. Okay, that is liquid gas interface. Flux will be zero flux condition. You can see here also exactly similar. Sometimes flux may be given at the surface in heat transfer also, and same boundary condition will be in momentum transfer also. Flux was given at the surface, and that interface that was more precise, and that was a zero flux condition when we will have a liquid gas interface. So that is what we are saying, that even though now we are discussing shell energy balance, so this is not different. Okay, this is similar. Only here velocity will be replaced by temperature, and moreover, what is the difference? Velocity is a vector and temperature is a scalar. In fact, this heat shell energy balance will be very easier. Here there will be only one energy balance equation. Here we will have x component, y component, and z component, because velocity was a vector. Velocity was a vector and temperature is a scalar. So here you need not to have worried about a three component. Okay, it will be just a one temperature, and its variation only we need to consider. Okay, so this is the second type of boundary condition. Third type of boundary condition. So here you can say at the interface there will be continuity of temperature and heat flux. Okay, there will be continuity of temperature and heat flux. This is exactly similar to modified no slip boundary condition. There there was a continuity of velocity and momentum flux. So modified no slip boundary condition. In addition, okay, because it is very common in heat transfer to have a convection. Convective heat transfer is there in association with conductive heat transfer. So additional some changes will be there. So this is solid fluid interface. When there is a solid fluid interface, there will be a convective heat transfer. Okay, at solid fluid interface, the normal heat flux component may be related to difference between a solid surface temperature and bulk of the fluid temperature if you have fluid. So now pipe is heated and surrounded by air. Okay, solid pipe is heated and surrounded by air at a temperature 25 degrees Celsius. So bulk fluid temperature is 25 degrees Celsius and say pipe is heated at 100 degrees Celsius. So normal heat flux can be calculated. How to calculate this normal heat flux in case of solid fluid interface? Here roll number 4, Aditya.
Yes, sir.
Yeah, if I have solid fluid interface, say solid pipe at 100 degrees Celsius and air, it is surrounded by air at 25 degrees Celsius. How to get a heat flux?
So we will be using Newton's law of cooling, like the heat transfer
Excellent.
coefficient into the difference of temperature.
Yeah, excellent, excellent. So here, this is Newton's law of cooling. So that is what I am telling that now we are equipped with all the information available. We have equipped or we have revised all the information in heat transfer, mass transfer, and momentum transfer. Now here we are applying the information. So this is not first time we are looking at this Newton's law of cooling in transport phenomena. This already we have discussed in detail in interface flux. At interface flux, okay. So now here we'll be using. That is what I am telling that now you need to be more attentive. You need to be more involved in this transport phenomena. Then only you will be understanding this transport phenomena. So these are the 4 type of boundary condition. And fifth type of boundary condition. What can be a fifth type of boundary condition? Here, Aditya.
Sir?
So
Hello?
can you guess a fifth type of boundary condition?
Sir, your voice is cracking. Actually, my network is not stable. So can you repeat the question?
Can you guess a fifth type of boundary condition which may?
It's a logical boundary condition in which we take some finite value.
Very good, excellent. So logical boundary condition is very important. Okay, and logical boundary condition says that I cannot have undefined value of measurable parameter in my system. Temperature is a measurable parameter, and I cannot say in my system my temperature is undefined. Okay, so that is illogical. That model will be illogical if I am giving some model equation which is giving me undefined value of temperature at some corner of my system. So that is logical boundary condition which we will be using when and where based on an equation. Okay, based on an equation and observing the equation and constant and everything, so that we can use a logical boundary condition. So these are all boundary conditions which will be used in heat transfer. So with this information, we'll start this problem solving. Now take down this problem. Okay, take down this problem is take out all the information, read carefully, and take out all the information. So you have 5 minutes to take out this all the information given in a problem. So write down carefully, read the carefully problem, and try to understand what it is, what exactly you are expected to do, what exactly you are you are given with the information in this problem. That is also very important. Given a problem, you should know exactly what information is given in a problem. If you take out the wrong information, certainly you will end up with a wrong output also. So consider a electric wire of a cross section with a radius r and electrical conductivity Ke ohm raised to -1 centimeter raised to -1. This is electrical conductivity. Okay, this is electrical conductivity. So you have electrical wire. Now you assume that So you have so many wire at your home or wherever you are sitting, so you can see the wire. So everywhere there will be wire through which electrical current is conducted. Okay, so if your fan is on, say your fan is on, so this electricity is coming to your fan through this wire, and we are talking about that wire. And generally, if say you have low load of low electrical load, then it will have multiple fine wires, winded together. But you consider that heavy load, and so a broad electrical wires, okay, with only one copper wire is there inside, and you may see in your home it is insulated with some polymer coating. Inside that there will be electrical wire. That electrical wire, that copper electrical wire we are talking about, it is not insulated and copper, only copper electrical wire. So the radius of that wire is R and electrical conductivity is Ke. Okay, this you can get it from data book. What is the electrical conductivity of copper? What is the electrical conductivity of copper mixed with brass? What is the electrical conductivity of aluminium? So all this information is available. So that is ohm per centimeter inverse. Through this wire, there is an electric current with a current intensity I ampere per centimeter square. So this is the current intensity. Okay, I ampere per centimeter square is, so I ampere per centimeter per cross sectional area, current flowing per cross sectional area, that is called as a current intensity. Okay, I is not a current, it is a current density. Current density means current flowing per unit area, per unit cross sectional area. So I ampere per centimeter square. The transmission of the electrical current is an irreversible process. So once electrical current is passed, you cannot reverse that current. Okay, you cannot say that, okay, now I have switch on a button, the fan is rotating clockwise direction. So now I will rotate the fan anti-clockwise and current will be flowing in reverse direction. It is irreversible process. Once it is used, converted to mechanical energy, and then converted, so many processes are there. So it is irreversible process. And during this current passing through this wire, some of the electrical energy is lost. So when current is passing through this wire, some of the electrical energy is lost, and which is converted into heat energy. Hence you feel, okay, if you touch a wire, don't touch bare wire, okay. Even if you touch an insulated wire, you will see that it is slightly heated up when it is used for longer time. Why? Because some of the energy is converted into heat energy. Some of the electrical energy is lost. While transporting, some of the heat energy is lost and it is converted into heat energy. The rate of heat production is given. Okay, rate of heat production per unit volume. Okay, rate of heat production per unit volume is related with the current density. This is not a current. This is current density ampere per centimeter square, and this is electrical conductivity, and this will be a heat production per unit volume. Heat production per unit volume, and this current density will be equals to, you can say, this is electrical conductivity and this is the potential difference or voltage drop. Potential drop or voltage drop per unit length. This will be a current density. So where E is a voltage drop over a length L, and this is the energy produced per unit volume. So energy joule per centimeter cube. Okay, joule per centimeter cube. So this will be energy per unit volume. If surface temp, now here the example is a bare wire, no insulation at all, no insulation at all. The surface temperature of wire is maintained at a T0 temperature. So say there is some mechanism using which I can maintain the surface temperature of wire T0. And the temperature variation is small because thermal conductivity, heat is transported by thermal conductivity and current is transported by electrical conductivity, and these are the function of temperature. But we are considering a temperature, there is a rise in temperature in this wire, but it is assumed that thermal conductivity and electrical conductivity is constant in this temperature range. So there is no very high. Say temperature is increasing from 25 degrees Celsius to say 50 degrees Celsius. It is so during from 25 degrees Celsius to 50 degrees Celsius, thermal conductivity remains almost constant. Electrical conductivity remains almost constant. Okay, there is a variation in temperature, there is a heat transfer, but this temperature variation is not so large to consider a variation in thermal conductivity and electrical conductivity. Derive the temperature profile and heat flux profile uh, uh, using shell energy balance approach. Okay, profile equation. First of all, temperature profile equation and heat flux profile equation using shell energy balance equation. So, roll number 6, Aksh.
Yes, sir.
Which coordinate system you want to use?
Sir, as the wire is circular cross section, so we would prefer that cylindrical one. Cylindrical.
Excellent. Cylindrical. So here now you need to use this shell balance in heat transfer is simple. Okay. Once you have selected the cylindrical coordinate system, fix the origin. So you need not to worry about temperature in x direction, temperature in y direction, temperature in z direction, because temperature is a scalar. So temperature is not associated with the direction. Temperature is temperature. While in this thing, momentum transfer, we have discussed velocity in x direction, velocity in y direction, velocity in z direction. Here temperature is temperature. Now we'll be just discussing a variation of temperature in what are the three directions? What are the three directions in cylindrical coordinate system?
Sir, R, phi, and theta.
No, cylindrical coordinate system.
Oh, sorry,
R,
sir, sorry,
phi,
sir, sir. R, Z, and theta.
R, Z, and theta. Now, just we need to worry whether temperature is varying in R direction, temperature is varying in theta direction, and temperature is varying in Z direction. So, roll number 9, Nitin.
Yes, sir.
So, what is your expectation? Now, you should expect whether there will be variation of temperature in R direction.
Yes, sir. Temperature will vary in R direction.
Why?
Sir, because heat is flowing in R direction.
Heat is flowing in R because you are saying that there is a temperature variation in R direction.
Sir, because of the boundary conditions, sir. The temperature is different at
Not boundary
boundary.
condition.
And
Look, here heat is generated. Here heat
Yes,
is generated and here temperature is kept constant.
yes, sir.
At the surface temperature is kept constant and here heat is generated. So certainly this heat will be flowing in this direction. So temperature is changing in this direction. Okay. So Nitin, whether temperature will varying in theta direction?
No, sir.
Why?
Sir, it is symmetrical around circular.
Excellent. Excellent. Whether temperature is varying in z direction? Nitin,
No, sir. No, sir.
why?
Sir, continuity, sir. Continuity.
Hey, here where is continuity, man? This is solid.
Yes, sir. Uniform.
So why
Yes, sir.
temperature is not?
Sir, uniform conduction of electricity
No,
in
no.
that direction.
Temperature is varying in z direction. Here, this direction. Temperature is varying in z direction. Now this is solid wire. This is not a pipe, and heat is not fluid is not flowing. Okay.
Yes.
This is copper
Yes,
wire, solid copper wire. So you think that okay, this is z direction.
Yes.
Okay. Here at z equals to 0, z equals to 1 centimeter, z equals to 2 centimeter. Whether you will feel a variation in temperature? Nitin?
Yes, sir.
Yes. but that can be neglected.
Yes, sir.
Why?
Sir, uh, because the variation is very low.
Variation is up to very small length.
Yes.
How to say that very more technically?
End
Yeah,
effects are
anybody?
neglected.
Ah,
End
very
effects are
good.
neglected.
End effects are neglected. So you can see that end effects are neglected is an excellent logical answers for many things, but you need to use appropriately. Everywhere you cannot say end effects are neglected because length is very large. So this variation of temperature in z direction is not penetrated through much length. Okay, it will be towards small length towards end and small length towards start, and that will be constant. Okay, so that end effects are neglected. Roll number 10, Aman.
Yes, sir.
So what will be the dimensions of differential shell?
The dimensions of a differential cell will be, as the temperature is varying in r direction, so we will take delta r.
R varies from R to delta R. Theta?
Z varies from 0 to L.
Very good. And
Sir, theta varies from 0 to 360.
very good, excellent. So, so there is only, because temperature is varying only in R direction, so there will be only one flux, that will be QR. Flux will be there in only QR direction. So, what will be the surface area perpendicular to QR? Roll number 11, Chetan.
Hello. Sir.
Surface area perpendicular to QR.
2 pi r into L.
Very good. So 2 pi r into L. That will be heat coming in. How to get a heat rate of heat coming in? Now there is no convection. Whether convection is there in this case?
No, sir. Conduction.
Only conduction is there. As convection is not there, work done because of molecular force is zero. Only and no heating is done. Okay, no heating is done by external forces. Heating is, there is a heat generated. Okay, heat generation. So now this overall this is, you can say, so there will be only energy flux in r direction. There will be only energy flux in r direction. This will be my differential shell. It will have a dimensions of delta r varies from r to delta r. Theta is 0 to 360, z is 0 to L, and this will be QR at R, which is coming in, QR at R plus delta R going out. This is by conduction, only by conduction. So this is overall energy balance equation. There is no convection because molecules are not moving. So this is there. Okay, as molecules are not moving, this is zero, this is zero, and there is no external addition of heat energy. Only rate of energy production is there. Okay, here rate of energy is produced because of loss of electrical energy, sometimes loss of chemical energy, sometimes loss of some energy. So this is there. So this is zero, this is zero, this is zero, this is zero, this is zero. So this is zero, convection is there. As convection is zero, so this is zero, actually this two is there, so external. So overall energy balance equation is this: rate of energy coming in by molecular transfer, rate of energy going by molecular transfer, plus rate of energy production. Okay, so how to get rate of energy production? So per unit volume is given multiplied by volume of a differential shell. What is the rate of energy production per unit volume given? Yeah, roll number 11, Chetan.
Yes, sir. AC is given, so multiplied by
multiplied by volume. What will be volume?
2 pi r into delta r into L.
Very good, very good. What? How to get rate of energy coming in by molecular transport?
Rate of energy coming in. Sir, QR at, acha, yeah.
Yeah.
This 2 pi r L into QR at R.
Very good. How to get rate of energy out by molecular transport?
2 pi r L into QR at R plus delta R.
Excellent, excellent. If you are able to, and you understood, yeah, Chetan, whether you understood why we are not considering convection and
Yes,
why
sir.
we are not considering these terms, whether you
Yes.
understood this and why it
No.
is zero. Chetan,
And
then it will be non-zero. When this RHS will be non-zero, what term will come instead of zero here? Chetan,
the accumulation term would be 0.
here we are dealing with a steady state problem, hence this is equals to zero. And
Yes,
hope
sir.
you understood everything why these are not there. So if now considering this problem, so rate of heat energy coming in across at the surface R, that will be equals to twice pi RL. This is surface area, and QR estimated at R. Okay, and similarly rate of heat going out. Okay, this is the arrow coming in, this is the arrow going out at R plus delta R. Surface area is same, twice pi R plus delta R. So delta R is smaller as compared to R. Delta R is differential, so I can neglect delta R as compared to R. So it will be twice pi RL QR at R plus delta R. And this rate of thermal energy produced by electrical dissipation. Here electrical energy is lost and some energy is converted to, and that will be volume. So what volume of the shell is twice pi R delta R into L into SE. So rearranging and substituting this in this equation. So what we will get? This we will get. Now here one most important point is don't shift the location of R, because QR is a function of R. QR is a function of R. QR and R is depends upon R actually indirectly. Okay, QR is a function of R, surface area. So that is why you need to you should not change the location of R, that we have done in cylindrical coordinate system. So divide the equation by 2 pi delta R into L multiplied by -1 and use the definition of differentiation. What you need to do? Divide the equation by all constant. This 2 is constant, pi is constant, length is constant, and a differential thickness. So 2 pi delta R into L, divide this equation by that, and then multiplied by -1. So this will be this minus this, and use the definition of differentiation. So you will get a differential equation which will be rearranging the equation. So this rearranging, so what we have done, we have divided this equation by twice pi delta R into L and multiplied by -1 and rearrange the equation. Now here we can use the definition of differentiation. Using the definition of differentiation, so limit delta R tends to 0. This is defined as d by dr of R into QR. Okay, d by dr of R into QR. So this is the equation. Everybody got this? Yeah, roll number 12, Anand.
Yes, sir.
Okay. So after integrating this equation, what you will get? Anand?
Hello. Yes, sir.
Integrate this
Like
equation.
RQR equal to SC into R squared by 2 plus C1 constant.
Yeah, and then you can shift the location and you can rearrange and get in the form of QR.
Yes, sir. QR equal to SC into R by 2 plus C1 by R.
Very good. Integrating and rearranging the equation, you will get this equation. So whether you have any boundary condition for this flux QR? Anand?
Sir, yes, sir. Logical boundary condition like at R equal to 0.
At R equals to, what is that logical boundary condition? At R equals to 0?
At R equal to 0, so QR should be finite.
At R equals to 0, QR should be finite. So hence
C1 equal to 0.
that is okay. You can say that C1, but now as we have used so many times, C1 should not be there in my equation. It is not C1 equals to 0. C1 should not be there in my equation. Okay. So that is logical boundary condition. So all these four boundary condition is not useful. So we will be using logical boundary condition. This logical boundary condition tells me that at r equals to 0, QR should have finite value. This is giving me undefined value, infinite value or undefined value. Hence C1 should not be there. Okay. Hence QR equals to SE into R by 2. Everybody got this equation? Yeah, Anand, whether you got this equation?
Yes, sir.
Okay. Roll number 13, Shiva.
Yes, sir.
What was the next step which we have used at identical same level in momentum transfer? What was the next step which we have used in momentum transfer? After getting a flux profile, which steps we have used in momentum transfer?
Sir, I'm not able to remember, sir.
Not able to download?
No, sir.
So we have solved so many problems. No? After getting flux profile, what is the next step? Correlating this flux with a property. So we have correlated flux with a momentum flux with a velocity.
Yes,
What
sir.
is that equation we have used? Which equation will correlate flux with the velocity?
Sir, flux with velocity.
Which
Sir,
equation will correlate, will give the relation between flux and velocity?
yes, sir. Newton's law of viscosity.
Newton's law of viscosity. We have used at same level in momentum transfer. So which equation will be using here? Which equation is similar to Newton's law of viscosity in momentum transfer is similar to which equation in heat transfer?
Sir, Fourier's law of heat conduction.
Yeah, very good. So you can see now that solving that problem and this problem is similar. There we are using Newton's law of viscosity. Here we will be using Fourier law of heat conduction. Okay. So after using this, so using Fourier law of heat conduction. What is Fourier law of heat conduction, Shiva?
Sir, here QR equals to minus K dt by dr.
Okay. Why there is minus sign?
Sir, because like the temperature, sir, the temperature profile to maintain the signs, like the negative sign will make the flux positive.
So here you are expecting temperature is increasing with R or temperature is decreasing with R?
Sir, temperature is decreasing with R.
Yeah, temperature is decreasing with R. So certainly this dt by dr will be negative. So hence this sign is there. So now substituting this, rearranging and integrating this equation. Integrating this equation. Roll number 14, Anmol. Everybody has done well. Now I got one only. 14 is not responding. Otherwise, everybody has responded. I am happy, very happy to.
Sorry, sir, there was internet problem, sir.
Oh, okay, okay. Oh, yeah, I will just come out. Okay, tell me. Integrate this equation. What equation you will get?
Sir, temperature would T would be equals to minus SE R square by 4K plus constant.
Plus constant. Okay. Integrating this equation minus SE R square by 4K plus C2. Whether you have any boundary condition for temperature now?
Sir, we have the temperature at the surface, sir.
So how to write that mathematically?
The temperature at R equals to capital R is equal to T naught.
Very good, very good. This is given actually, and that is a type of boundary condition. What is that? A type of boundary condition, temperature is specified at the surface. At R equals to R, temperature is maintained at T0. I'm substituting this, I will get a constant value. So C2 equals to SE R square by K plus T0. Now substituting this value in above equation, so what temperature profile I will get? T minus T0 equals to SE R square divided by 4K 1 minus R by R square. So you can see this is exactly similar to velocity profile for flow through. Okay, this is temperature profile. Once I have temperature profile, what I can get is the maximum temperature. So Sai, roll number 15. Sai.
Hello, sir.
So where you are expected to get a maximum temperature?
Sir, at R is equals to 0, sir. At the center of the wire.
So at R equals to 0, what will be maximum temperature then? That will be at R equals to 0.
Yes, sir.
If you put 0, so it will
Yes,
be
sir.
1. It will be
T naught
SE R
plus
square divided by 4K plus T naught.
plus T naught. Yes, sir.
That will be maximum temperature. So you can get
Yes, sir.
average temperature also. So this
Yes,
is
sir.
maximum. This is a temperature profile and flux profile. So this is maximum temperature at R equals to 0. So T max. So this is very important. If I know what is the heat generated for a given current density, so I can get a maximum temperature that can be reached in my given wire. Okay, and this is very useful to design an insulating material for the wire. My insulating material should be operated efficiently at this temperature, not at this temperature. Okay, this temperature will be considered, this maximum temperature will be considered to design the material for insulation. Hence you will see that, okay, that high current flowing wire, high tension wire, that is called as a high tension wire, have a different insulating material because their heat generation is higher as compared to heat insulation in our household wire. And the cost of wire will also vary based on this polymer which you are using for insulating material. And this is very important property based on this maximum temperature which can attain given a current intensity and a potential difference. So the thermal conductivity and radius of wire, I can calculate what can be the maximum temperature that may go in a given wire when there is a current flowing through that. And based on that, I can tell that, okay, this insulating material is good or not. Okay. Then we can have so many properties. Once I have temperature profile and flux profile, I can have so many properties. Then average temperature rise. So I can average it out. What will be the average temperature rise? So this will be average over 0 to R. It is not function of 2 pi. So you can take it out constant. So this will be average temperature, average over cross sectional area, that will be equals to SE R square divided by 8K. That, and this is flux profile. So I can calculate the total heat flowing out from the wire. What will be, how to get that? So I can get a flux at surface. What will be flux at surface? Heat outflow at the surface. This will be a heat flux at the surface multiplied by surface area. So this will be a rate. Okay, this will be a rate, flux multiplied by rate, and that, okay, this is what at R equals to R, and substituting this in this equation, I will get a rate equals to pi R square L into SE. This will be a rate of heat flowing out from the wire. Okay, everybody got this? Anybody has any confusion in this problem? Just quickly, I will go through all the slides for this problem. If you have any doubt on any slides, okay.
Excuse me, sir.
Yeah, tell me.
Sir, I was just thinking, yes, sir, 85. Sir, I was just thinking crudely that when we consider this flow of current through a cylindrical wire, we can just say that H is equal to I square RT. So it is depending directly upon R. So we can neglect other coordinates like theta and Z.
H, heat transfer coefficient you are telling?
No, sir, heat generation. H is equal, capital H is equal to I square RT.
Yeah. Anyway, because just to have some feel that heat is generated through wire, this current and potential difference is added in a problem. Okay, so that you can do anytime, but here generally this case, so you should correlate, no? Because we are solving some virtual problem. This is also virtual problem, so some physical view or physical field should be there. Hence, this current is added, potential difference is added. These model equations are not wrong actually. These are actually used. Okay, so you can use that also.
Sir, and also if, hello, sir.
Yeah, tell me.
Sir, also like to add more to this discussion, like if we consider that it is a long wire, very long wire, so there would be a temperature gradient across the length.
No.
So,
no, there will not be temperature gradient across the length.
Okay, sir.
Why there will be temperature gradient across the length?
Sir, I was thinking that since it is a very long wire, the heating effect would be very slow.
Heating effect? No, look, you if say wire is say 20-meter long.
Yes, sir.
Okay, leave aside a first 5 centimeter and last 5 centimeter. And now you think that whether there will be any parameter change in z direction.
No, sir, there would be not. One more thing came to my mind, like current it passes through with the speed of light. So heating effect will be same. You're right, sir.
Yeah, but it will passes after 5 meter, after 5 centimeter also speed of current will be same. At the end also speed of current will be same.
Yes, sir, it will be same.
Okay. So just I will go through, and if anybody has any other doubts. Just quickly revise this, and if you have any doubts, you can discuss. Okay, then if you have any, you don't have any questions or any doubts, so you can leave the class. We'll continue with next problem in tomorrow's class. Okay, thank you very much.